Welcome to my Texas workshop. I'm Randy Lammers.
I'm Keevan.
This is Würth Knowing. So Aaron, today we're going to talk about screws or plastic assemblies. Very big subject. We're dealing with a lot of this today as more and more companies are turning towards plastic materials. So in that, we have to talk about the screw boss design. We have to talk about the different thread designs that are out there, because make sure you get the right thread for the right application. And assembly performance. How do we assemble these things?
There's some challenges there. You know, you've got to worry about your material cracking, the stiffness of the material itself, relaxation, and also the assembly speed. And so the goals obviously would be to reduce our stresses, would be to maintain a sufficient clamp load. And just like every application, we want to make sure that we have a robust assembly.
Absolutely. So let's start with materials. And the difference in the materials, because plastics are evolving, and the plastic is a very broad term. So there's a lot that goes into plastic materials, and every day it seems like our customers are saying, well, I made this little change in my material today, and that changes how the screw performs. So let's talk about that. So first, we're talking about thermoplastics. And they fall in different categories based on what we call the flexural modulus.
That's a fun word.
Flexural modulus. It took me a while to figure out how to say that.
Say that 3 times fast.
So in the thermoplastics, you kind of start with your more softer materials like the polypropylene, maybe ABS. Then you get on the other side, which is in the polycarbonates that are in the like 1 million PSI plus. Yeah, that's really up there in stiff materials. And the glass filled materials. Anytime you start adding those fillers, that changes everything. So change the screw to go with the plastic. Now, we get into thermosets. That's a whole nother ball game, and you're not going to thread form in the thermosets. It doesn't flow well, so we thread cut into the thermosets. It's a little bit different going on that. But let's talk about the thermoplastics just a little bit more and what those screw designs are. So let's take a look at the kind of evolution, if you will, the evolution of thread. So we started off, what do you see out there in old material all the time, Aaron? Well,
they're using tapping screws.
Sheet metal screws.
Sheet metal screws, right?
Exactly. I can't tell you how many times I've seen customers take, all right, let's look at this. Type B tapping screws, sheet metal screws, type B, type AB. Then eventually over time someone said, hey, look at this drywall screw. I can take this high-low drywall screw. It is a thin thread and a small root diameter, and they start putting those in. Those actually work pretty good. Then it was the tri-roundular screws. So these screws work good in metal. We did that program. On the tri-roundular screws.
Yeah, it works great. Pushes the material aside and you can get that thing to seat in correctly.
Exactly. And so that works good in the softer plastics, not so good in the stiffer plastics. So we have the tri-roundular screws. And then eventually we start evolving into the higher performance thin thread screws, get away from that 60-degree flank angle on the regular sheet metal screw.
And you've got a little bit of difference and some commonality, at least with those types of threads. So you got a 60-degree angle on, your typical tapping screws that we use in metal, or machine screws in tapped holes. But you also have for the plastic screws used for plastic assemblies, you've got a 30-degree angle that's used. It's very thin thread. And that's a commonality in those types of screws.
And the whole idea about thinning that thread out is putting less stress in the wall of the plastic. Plastics don't take stress very well, so reduce those stresses. Now, let's talk about performance versus strength. So we first started coming out with this. We mentioned the drywall screw. So it has a lot of thread that goes into the side walls of the hole, but it has a very small root diameter. And some of the multi-angle screws that first came out on the market also had that small root diameter. They perform really, really well. Relieves the stresses, but because of the small diameter, they are weak. Then you have the strength category. Full root diameter, a little bit larger on that, good thread designs, not quite as good as the performance on the other side. We finally now have on the marketplace today a couple of designs that bring both of those together. I have the performance and I have the strength, and that's where we're leading our customers to, is that right there.
Built for comfort.
Built for comfort. Yeah, comfort in assembly.
Yeah.
Knowing that I can put these screws in and I'm building a product that's robust that will last forever. So Aaron, let me tell you about what happened with one of our customers in plastic assemblies. And this is really a critical thing that we need to understand. So they had a plastic component they were very happy with, but needed a few changes, so they made a plastics change.
Okay.
They then were using the same screw they've always used, which happened to be a triroundular screw. And when they put that screw in there, it cracked the plastic. So rather than coming to us, which they should have done, they went to the plastic supplier and said, your plastic cracked. It's kind of like the screw's always bad. Yeah, the plastic. So they went to the plastic supplier and said, plastic cracked. First thing they did is said, well, what screw did you put in there? They showed them the triroundular screw, and they said, that doesn't work good in this high modulus plastic. They knew what they were talking about. And they suggested they put in a twin lead high-low screw. Right. Fantastic, works good in the plastic, but what that plastic manufacturer didn't understand is the application. This gets put in there, gets out in the field, and screws start backing out of the plastic. This caused them to have to do a recall for millions of dollars it cost them. Millions. All because the wrong screw for the plastic and for the assembly. We always try to understand the whole assembly. Again, it's performance, strength, and long-term use.
Right. The twin lead threads in high vibratory applications, they tend to back out. So we have to be very careful and really look at how is this going to be used in service.
Right. It's the steep helix angle. So if you take a look at the helix angles of a single lead versus a twin lead, it's the steep helix angle that causes that vibratory back out. So know your assembly. Not only know your plastic, but know your assembly and how it's going to be used. Yeah. That was a story I'll never forget.
Right. So Randy, you mentioned triroundular screws. So I've got an example over here that I'd like to show you, and maybe you can explain what we've got going on right here.
The triroundular screws, they're good in certain plastic materials. We're getting a high flexural modulus, like our example we talked about. What that does, that lobing, that triroundular lobing, creates a high stress to the sidewalls. In high flexural modulus plastic materials, that's too much stress. So we have a piece we had around the shop here that we put some triroundular screws in, and what you're going to see here is what we call hoop stress. So you see kind of a whitening around the screw right here, and you have a line right here. That'll continue to crack out over time, and that's what happens. So if you ever see that hoop stress taking place, you have an assembly problem. Now think about this. If I do this in like a whole component like this, I have to throw that away. That's just waste, Aaron.
Starts to cost a lot of money.
It costs a lot of money. So we can't make that mistake. Now grab that other one. So we'll show them this one right here. So this is one of the newer design screws with the multi-angle on it. And what you're going to notice is when we put this screw in, there's no hoop stress, no whitening of the material. This high flexural modulus material took that screw very, very well with reduced stress. So let's talk about thread design now. So the latest designs, what they've done is multi-angle. And we have a couple of different designs that are really good at this. They have provided stress relief areas. So when the plastic flows between the threads, it gives an area for that to relieve itself. The stress relieves it. So one design relieves it at the root diameter. The other design relieves a space area out there in the flank angle for also stress relieves. So two good screws. The automotive industry has accepted both of those designs as alternatives to each other. Works very, very well, and works in all of the plastics with the exception of thermosets that you have to thread cut. So it's worked very good. So we're trying to teach this to more and more of the customers out there that are designing in plastic materials. Let's just go to these screws to begin with, and we don't have to worry about it.
Exactly. And that's why you have to look at minimizing your clamp load instead of maximizing it. And then we also have to be concerned with the assembly speed. So typically you're looking at what, 500 to 600 RPM is your range for most of these screws.
stay.
And it's really dependent on the material and the diameter of the screw.
Exactly.
So, yeah, you keep going back. It's going back to that plastic every time.
Let's talk about assembly speed for just a second. So whenever we know that we're dealing with fast-paced assemblies, most of our customers are making lots of components, especially if they're making small components like this. They're running them fast through the assembly line, low-cost items. So, but on putting those screws in, keep your RPM below 600. Every time you speed that up, what you're doing is you're melting the plastic. Right. And you can do this sometimes, and you can take that plastic screw out, and you'll notice if you do that, and you notice you have melted plastics in those screw threads, your RPM is too high. Yeah. Now, the other thing that this does to you, Aaron, is it changes then what you get your strip out. So you strip the plastic out. So if you're melting the plastic, it strips out a lot faster. Sure, and you don't want to do that. So think about this. If I took one of these pieces like this right here, and I stripped out these holes, that's now junk. That goes to scrap.
Yeah.
And that's expensive. Yep. So we can't go down that road.
Yeah, it sure is.
Now let's talk about the boss designs, the screw boss designs. And this is what we're talking about right here, is screw boss design. So we can give you good data on the material that you're using as to what your outside diameters need to be in order. That's a robust design for an outside diameter, enough material, but we can minimize those materials now, save you money. Also, inside diameters, what they should be, and critical is what we call a counterbore.
Right.
What do we see too often, Aaron? Every time we do assemblies, countersinks out there. So engineers get counterbore, countersink mixed up all the time. Please don't do that. The countersink is an angle like this. You put that in there if you want to put a countersink screw. Counterbore straight wall, a little bit larger diameter. It's at the top of the screw boss. That gives you a relief area, and that's what you're looking for. It's really critical to the total design. It allows that thread to flow into that area and relieve the stresses you're putting in the plastic. So counterbores are important. We can give you full screw boss design data to go with this.
Right, so Randy, one great benefit is you can actually eliminate brass inserts.
Absolutely, yes. So we have parts that commonly we have brass inserts because maybe we're using the screw repetitively in and out use. Some assemblies in some plastics, you can remove the brass insert that's been molded in. So that saves you time in your molding operations and the cost of the component itself. Let me show you something really cool.
All right, let's see it.
Hey, grab my tool over here and look at this. So this is that high flexural modulus material that we cracked earlier with the tri-roundular screw, and this screw design did not do that. What's another feature that's really good about this is that, look at this, Aaron. Let's just go ahead and take it all the way out. And look at those threads.
Yeah, perfect.
Really good internal threads.
Nicely formed.
And then I can put this screw right back in its place. And I've done this several times on this piece of material right here in order for do the show, and I can go in and out with this screw. So this works really, really good. Some materials, be careful with that, maybe do need brass inserts, but then some materials do not. Now, if I'm going to take this screw in and out every single day,
yeah, you're going to have to stick with those brass inserts.
Probably go with the brass inserts. They're typically molded in. But if not, over the life of the product that I have, I need to take that screw out maybe a dozen times. Hey, let the screw do the work. So in conclusion, Aaron, screws for plastic assemblies. Lots of plastics being used out there, or have been used out there, and newer and newer plastic materials that need the right screw in them.
For sure.
So with that, let's stay with our thin thread designs, our special angle thread design. So watch your thread profile.
Yep, or your twin lead threads. You just have to worry about basically the material there. So avoid that if you think it might be an issue.
Due to vibratory backout.
Yeah, exactly.
Yeah, and those kind of assemblies. And then also the tri-roundular screws. So they work good in your low flexural modulus materials, but get into higher flex, be careful with those screws.
Yep, control that assembly speed. Obviously can't go too fast, you're gonna start melting plastic.
Yeah.
Yep.
Torque, we've talked about torque. Torque and clamp load. Keep your clamp load down. So clamp load creates stress in the plastic. So only do what is needed for your assembly. Do not maximize, optimize.
Yep. Choose the proper boss design. Use a counterbore and not a countersink.
Yes, please.
Yep.
Stay counterbore on these straight wall counterbores to relieve those stresses.
Right. So some of the benefits we have, Randy, we have reduction in material stresses, use of smaller bosses, improved assembly performance, and reusability is possible on some of these screws.
Exactly. So for good performance on your designs, choose the right screw for the right plastic you've chosen for your assembly. The right screw for the right plastic material, that's worth knowing.
If you like the content you saw today, hit that subscribe button and the bell icon, and we'll see you next time.